1102, chapter 22 on electromagnetic waves. All right, this will be the final chapter of 2 for exam 3 coming up. So, based on the shortness of both chapters, I probably will not be doing an actual review for exam 3. So, exam 3 will be on chapters 21 and 22. So, let me start here. So what we do is electromagnetic waves include light, UV, infrared, X-rays, radio, microwave, and all the way down to 60 hertz power lines. So that's all of electromagnetic spectrum as far as that is concerned. There's a nice thing on that, but we'll get to that in a minute. Light, we talk more about waves. We have in the past talked about when we did sound waves. All right, sound, when I talk, are what we call compression. They vibrate back and forth. So if the wave is going this way, they vibrate back and forth like this. Light, on the other hand, are transverse. And we'll see this when we do lab 9 coming up next. And those vibrate perpendicular to the direction that it's going. So the wave is doing this, it's vibrating up and down like this, but transmitting that way. There's a good picture in the text about that. The fact that electromagnetic wave is actually composed of perpendicular, magnetic field, and electric field. So if we actually look at this, and let's eliminate this for now. So it's actually a propagating electromagnetic field, and so what we'll actually see is that light is what we call transverse, and normal sunlight is what we call unpolarized. So it's vibrating actually in all directions as it's coming towards you. So that's what we call unpolarized light. And we'll get into the lab when we talk about lab 9. When I do lab 9 later this week, we'll be dealing with that issue too. And from there, all right, so that's what we call unpolarized. So it's actually, as it's coming towards you, it's actually many different light photons. We'll get into this. So light is made up of individual photons, and that's part of what we'll talk about when we get into the properties of the nucleus and things like that. But this is what we call unpolarized light. Polarized light is vibrating up and down in one direction. So it can either be this way or that way. So this week, polarized light. And this can be whether it's anything. So for the lab, we'll be dealing with visible because that's the easiest to deal with. Now all light, the speed of light, V, is given by the letter C, and it's 3 times 10 to the 8th meters per second is the speed of light. So all light, including the entire electromagnetic spectrum, goes at that speed of light. Okay? Now this picture, this describes it extremely well. As far as the electromagnetic spectrum, you can see on the far left we have 60 hertz, very low frequency. And very long wavelength. On the other end we have gamma rays. And then in the middle we have visible light ranging from visible light, so that's our speed of light, visible light, and if we do what we call Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, that goes from the low wavelength of approximately 7 times 10 to the minus 7th meters, all the way up to violet, which is approximately 4 times 10 to the minus 7th meters. And based on the fact that the relationship between speed, between speed, which in this case is C, equals frequency times wavelength. This would lead to, this is a wavelength of that. This would be a frequency, I'll just quote from the book, 4 times 10 to the 14th hertz. And this is 7.5 times 10 to the 14th hertz. So that the product of these two gets you that. All right, so that'd be approximately 7. So the product of these two, this times that gets you speed of light. So as the wavelength gets shorter, you get higher energy, the frequency gets higher. So that's what we have there. And again, visible light is right in the middle. Long wavelengths, low energy here. High wavelengths, short wavelengths, high energy on this side. All right, so there will be using this expression then. What we've done before, so it'll be relationships between, if I'm given a certain wavelength, say microwaves, what would be the frequency of that? Okay. All right. Again, there's not a whole lot in this chapter as far as X is concerned. So one of the biggest expressions is this one here. And yeah, for this chapter, okay. Section 22.4 as a brief history on measurement of speed of C. So it goes back to the fact that all the way back in the 1670s, old Romer was able to estimate rather accurately the speed of light by observing the moons of Jupiter as they appeared, and the fact that they were delayed based on how far Jupiter was either close or near Earth. So it was this kind of dilemma, this inconsistency with the measurements as he expected led him to realize that the speed of light was not infinite. All right, so that's that part. Again, there's not a whole lot in this chapter, but that's okay. So I want to move on. So this is expression, those are the values there. All right, now what we're going to do is, the last part here we're going to be doing, 22.6, is radiation pressure. And this is an interesting concept because this deals with the idea of solar sails. And also the fact that there's a solar wind. But generally the fact that light exerts pressure, all right? Now we have pressure, we have weight, a certain amount of weight over a certain area, it's going to exert pressure. We have pressure, P is force over area. So that's the pressure, this is the force, and that's in units of newtons per meter squared. Light does the exact same thing. If we have, say, sunlight, light exerts pressure. So the light coming out exerts the pressure on, say, a sail or whatever, and yeah. So, but before I get to that part, the intensity of sunlight, right? The intensity of sunlight is given in units of watts per meter squared. So it's how much power over area. Now the sun, just to be on, just approximately, the sun emits approximately power of about 10 to the 26th watts. All right? Yeah. Yep. So, based on that, at this Earth's surface, the pressure, the intensity is given by the pressure power over the area, and at a distance of, the distance from the Earth to the Sun is approximately 150 million kilometers or 150 billion meters. The intensity at the surface of the Earth is approximately 1,000 watts per meter squared. So approximately 1 kilowatt per meter squared. So that's the sun's intensity. So if you have solar panels, that's how much energy is delivered per meter squared at the Earth's surface. So I'll leave that up for a minute. I'm not going to answer this question. I'm just using the fact that the sun's radiation, because it goes out as, the intensity goes as the radius squared. You double the distance, the intensity is 1/4 as much. All right? And we'll see that with the Lab 9. And we did this with sound last semester. So intensity goes as 1 over the distance squared. All right? So if you're twice the distance from the sun, 300 billion meters, intensity would be 1/4 as much, or about 250 watts per meter squared. So that's that part there. All right, so that's the sun's intensity. And moving on from there, this concept of power, pressure. Yep. So pressure, solar light pressure is given as the intensity over C, or it's given as the power, so this is pressure the intensity in units of watts per meter squared, which is also equal to the power divided by the area time equals C, divided by C. All right? And this is the expression for non-reflective. If we have a reflective material, like a nice aluminum sheet, then if we have sunlight bouncing, it bounces back, the pressure is given by 2I over C. Okay. So, all right, so let's do a simple example. All right, so let's say we have at the distance from the sun of the Earth, the intensity, so this is the Earth, we're here, and we want to put a solar sail out. The intensity is 1,000 watts per meter squared. All right? So the pressure which is force over area will be given as 2I over C, which would be 2,000, 2 times 1,000, over 3 times 10 to the 8th, which should be, let's see, that'd be 20 times 10 to the 6th. Yeah. So that's approximately 6 times 10 to the minus 10 to the minus 6th newtons per meter squared. So that's the pressure exerted at the distance of the Earth from the sun. So it's pretty small. So I'll give an example of what kind of actual force it would be. All right, so I'll leave that up. Here's our expression for pressure for a reflective surface. This is pressure for a non-reflective surface. It's going to be I over, so it's the pressure in watts per meter squared, intensity of watts per meter squared divided by C, where again C is 3 times 10 to the 8th meters per second. So, let's say we want to do a solar sail. You may have heard something like that. And we put out at the Earth, so we launch a square, say 100 meters on each side. So it's basically a football field on each side, which is pretty large. And you have it exposed to the sun, where the intensity is 1,000. So again, I is 1,000 watts per meter squared. This area will be 100 times 100, which is 10,000 meters squared. All right, that's the pressure at this point, P. The force, remember pressure is force over area, so implies force is pressure times area. So in this case, we can find the force. We have this much pressure on a sail that big. The force will be our 6 times 10 to the minus 6th newtons per meter squared times 10 to the 4th meter squared, gets us with 6 times 10 to the minus 2nd, or 0.06 newtons. All right, so that's a pretty small force. To give you an idea of that, let's see here. Let's eliminate this for a minute to give you an idea. All right. Excuse me. 1 Newton is about 4.5 pounds. Right? Is that right? 1 Newton. No. Let's see. 1 kilogram is about 10 newtons on the Earth's surface. And so 1 pound, since 1 kilogram is 2.2 pounds, 1 pound is approximately 4.5 newtons. So this is about 1/4. So this is to be just kind of move it over 2 decimal places. This is about 1/100 of a pound. So that's a very tiny force. So the sun's force on a square, 100 by 100 meters, would be this kind of force. Very small. So we need this actual Newton force. So this is our pressure. Pressure is given in P in this units. And that's why if they have a solar sail, you're gonna have to have a very large sail. So that's the last part of chapter 22, and that's all there is to it. So again, I'm not going to do a specific review for exam 3. So just because both lectures are relatively short and the sections are relatively short as far as that's concerned. So if you look at the review quizzes for both chapters,